Homework's checked off in your folder. You got your quizzes back. And just taking a look at where we're going. Today we're going to have a lesson on interpreting derivatives. Monday, your trucks project is due. So Monday is trucks, and sorry if any of you had a panic attack because the packet said it was due today. Sorry if you noticed that. Always go by the syllabus if there's a discrepancy. So Monday, your trucks project is due. Wednesday, we review for the test. Friday of next week, week from today, is test 1. Okay, so one more time. Project 1, your trucks project is due Monday. All right, so today in class, we're going to learn some different notation for the derivative. We've actually seen it, but we're going to formally talk about it today. And we're going to explain what the derivative represents in a variety of contexts. So this section is a little bit notation heavy. Stick with it, and the symbols will become second nature with a little time and effort. Okay. So a little bit of history about calculus. It was invented or discovered, however you want to think of it, independently at the same time by 2 different people, Leibniz and Newton, around 1660. So they invented or discovered this concept of calculus, but they had different notations to express the concepts that they were working with. So Newton wrote the derivative of x squared plus 7 by writing x squared plus 7 with a dot over it. And that meant the derivative of x squared plus 7. That notation is not used that much, although I have known some European mathematicians who use that dot. So it's not, you probably won't see it unless you meet a European mathematician. Okay. Leibniz used a notation dy dx to represent the derivative of a function y with respect to x. And about a century later, the French mathematician Lagrange was the one who invented the prime symbol, f prime of x, to represent the derivative of f. Okay, so there we have 4 things that all mean the derivative here: f prime of x, d dx of a function f of x, dy dx, and y prime. Okay. They all mean derivative of a function. Right, so one disadvantage of Leibniz's notation is that if you wanted to write the derivative evaluated at 3, with the prime it's really easy. It means you write f prime of 3. That's the derivative of f and plug in a 3. With Leibniz notation, you have to write it dy dx, and we put this vertical line that means evaluated when x equals 3. So it's just a little bit more cumbersome to write that. So dy dx came from the fact that the derivative, graphically, what is the derivative again? The slope of the tangent line, right? And traditionally, we calculate slope, right, as change in y over change in x. Right? So let's go back to our picture that we've talked about many times. Right? So here's some function y. Right? And if I want to know the slope of the tangent line right there, I pick another point on the curve and I calculate the slope of the secant line. Right? And then I let those points get closer and closer and closer together. So the slope of the secant line is the change in y over the change in x. And then as we take a limit, as those 2 points get closer together, we change the notation. Instead of delta, we use a d. And it just sort of represents we're taking the slope of 2 points that are infinitesimally close together. So we change the delta y over delta x becomes dy dx as we take that limit. So that's dy dx. It kind of reminds us that this is a slope. And it has units, y units over x units, right? Because delta y over delta x, y units over x units. So, or if we're dealing with variables other than y and x, it has units dependent variable units over independent variable units. So for example, if G equals F of T represents the cumulative number of gallons of water that have passed over a waterfall T seconds after midnight, then dg dt has what units? Gallons per second. Yeah. Yep. dg, like, so G units are gallons, and my T units for time, those are seconds. Gallons per second. So dg dt is measuring a rate at which the water is going over the waterfall, measured in gallons per second. All right, so in the context of this same waterfall example, no derivatives involved here. It just says G of 30 equals 120. What does that mean? Seconds. 30 seconds, 120 gallons have gone over the waterfall. Yep. Right, because T is my independent variable here, time, so 30 is a T. So at 30 seconds, 120 gallons. Gallons has or have? Gallons have, I think. Gallons have passed over the falls. Okay, so now I've got another one. This one does involve a derivative. This says dg dt evaluated when t equals 30 is 3. So dg dt, that's a derivative. Its units are gallons per second. They gave me t equals 30, and I get the output of 3. Okay, so what does that statement say? That's the rate that the water is going over the falls. Yeah. Very good. At 30 seconds, the rate at which water is flowing over the falls is 3 gallons per second. Are people still writing that? Ready? Wait a second. Okay. All right, so now we've got a different example. Now R is going to be dg dt. So I'm calling dg dt its own function, R for rate, right? Okay. G is the waterfall function above. So what are the units on dr dt? Like the derivative of the derivative. Gallons per second. Yeah. Yeah, because the units on R are gallons per second, right? We already figured that out right here. dg dt's units are gallons per second, and R is dg dt. So my R units are gallons per second. Okay? And then my T units are seconds again. So this is actually, you can think of it as gallons per second, or a lot of physics people like to write that as gallons per second squared. So this tells you the rate at which the rate is changing. Right? What special word do we have for that? Acceleration, yeah. All right, so what does dr dt evaluated when t equals 20 equals -2 tell us? Per second. 2 gallons per second per second. Oh, per second squared, yeah, good. Okay, so the rate at which water is going over the falls is changing by 2 gallons per second per second. So this is telling us that the rate at which the water goes over the falls is not constant, right? It's not just moving at the same speed all the time. It's changing, decreasing by 2 gallons per second every second. So 1 second, right? So in the previous example here, at 30 seconds, it was going over at 3 gallons per second. Right. 1 second later, 31 seconds, how fast is it going over according to the acceleration? Close. You added 2, you should subtract 2 because it was negative 2. Yeah, so it's going over 1 gallon per second a second later. Does that make sense? I'll write it all out in a sentence. Okay, so the rate at which water goes over the falls is slowing down by 2 gallons per second every second. Every second that passes, the water going over the waterfalls is slowing down by 2 gallons per second. Okay, so derivative can represent rate of change in many, many, many contexts. I'm going to have you explore some in your group activities.